Let's talk about friction. We think friction is due to the interlocking of molecular hills and valleys between a surface and an object sitting on the surface. Even your lab tables, for example, although they may appear smooth on the atomic level, when you zoom in, they aren't. They're jagged surfaces trying to slide across each other. Here is the key idea for the direction of friction. Bruce, this is what you want to underline. Friction resists sliding. Whichever way the object is trying to slide, point friction in the opposite direction in your free body diagram. Because it resists sliding, it can resist motion, like when you're trying to slide a heavy object across the floor, but it can also create motion. So example 1 says, draw the direction of friction in each case. Here's a sliding block. These documents were typed up, I think, in Word 95 for Mac, and the graphics are getting a bit glitchy. It might look like this block is floating on air. It shouldn't be. I'm just going to go color, 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 color. Oh, I'm going to go color, color, color. There shouldn't be a gap. Really? There shouldn't be a gap there. Okay. Ready? Which way is friction? Ahmad, which way is this block sliding? To the, give me a word that starts with letter R. Which way is friction going to point? Yep. That's the most intuitive and easy one to figure out. It gets trickier when you look at things like cars. When you step on the gas, when a car starts to speed up, which way do the tires push on the road? Yeah, the tires push that way. In other words, they try and slide that way. Forces come in, pairs. There's going to be an equal and opposite reactive force forwards. What force is that? That's friction. Friction resists the sliding that the tires try and do. So here, friction would push forward, would be pointing forwards. Technically on both tires, I'll just assume it's a rear-wheel drive. By the way, that's why when you step on the gas really fast, your car spins. Now it's no longer sliding, there's no friction. That's why it's worse to have your car spinning. You want your car tires not spinning. You'll get way better acceleration. What about when you slow down? When you tap on the brakes, which way do your tires apply a force on the road? Which way do they actually try and slide? They try and slide forwards. The tires apply a force that way. And because forces come in pairs, friction is a Newton's third law reactive force, it's going to push backwards. This is why, Carly, I keep saying the force that makes a car go forwards and the force that makes a car stop, both friction. Let me pause the video for a second. So, friction resists sliding. Let's talk about how we calculate it. So what does friction depend on? It depends on the types of surfaces that are in contact. Sandpaper in contact with other sandpaper, high friction. Teflon, low friction. So here's a new symbol for you. The number that describes how slippery or sticky is called the coefficient of friction. This is your new terminology here. And the symbol is the Greek letter mu. It's this thing. Okay? When you see a mu in physics, almost always, not always, because we do run out of letters, even Greek letters, but usually that's a number that describes how slippery or sticky an object is. It has no units. It's just a ratio. If mu is big, lots of friction. If mu is small, slippery. Usually mu is between 0 and 1, but not always. We'll talk about situations. Well, more than 1, that's glue, if you want to be honest. Steel on ice has a coefficient of friction, a mu of about 0.01. Rubber on concrete has a coefficient of friction, a mu of about 0.75. Although this one depends on weather. Hotter concrete is stickier for various reasons. So in our equation, that symbol should show up. What else does it depend on? Initially, Robin suggested mg, Mr. Dueck, but I wanted to explain why it is when you lift up, it's easier. When you push down, it's harder. What force is changing when I lift up or push down? What? Here is your equation for friction. In fact, this is the last equation for this whole unit. It is on your formula sheet. Friction is mu times the normal force. It's how sticky the object is times how hard the two surfaces are being pushed together. This is one of the few times, maybe the only time, Terrence, when for some reason I write an extra letter. Every textbook abbreviates friction without the R. I don't know why, but when I started teaching, I started putting the R there, and it's a habit I can't break. It's the only time, Carly, probably ever, that you'll see me write an extra character unnecessarily. If you use FF, I'll know what you mean, and you can choose to use that. But for some reason, I just can't shake the F. I got to put the R there. I don't know why. Okay? Friction is mu, the coefficient of friction, times the normal force. Example 1 says this. Suppose we are pulling a 6.5 kilogram mass across a rough surface with a coefficient of friction of 0.64 at a constant speed. How hard do we need to pull? What's the key phrase in this question, Nyla, that I should probably underline? That's one thing. There's another key that tells me friction. What's another key phrase? Keep reading. What? What's constant speed tell me? Forces are. I'm looking for a word that starts letter B. Okay. What's it asking me to find, Nyla? Just read me the last sentence. Yeah, how hard I'm pulling on the rope. You know what this is a good job for? I'm going to do a free body. Although, did they give me a picture? I'm going to label the picture, which technically isn't a free body diagram because you're supposed to represent the mass with a dot. Generally, moving forward now, if they give me a picture, I'll probably label the picture. So, Nyla, what are the forces acting on this object? Get the obvious one. Which way? Is this object sinking into the ground like quicksand? Is it flying to you like Superman? So vertically, forces must be, I'm looking for a word that starts letter B. So there's got to be an arrow pointing up the same size as mg. What force is that? Well, it's the ground preventing you from sinking into it. What name have we given to all of those types of forces that prevent an object from sinking into them? I'll give you a hint. It appears in the friction equation. Yes. What else? Well, someone's tugging on this rope. I'm going to give you a new term. In fact, we're going to write it in our notes in a little bit. We have a mystery force coming from off the page. I don't know if there's a person over here or a machine over here or invisible leprechauns. You know what? I don't care. When we have a mystery force coming from off the page, we usually call that an applied force. We say something's applying a force. And so typically we would label this force here F applied, F-A-P-P. That looks like F-Q-P-P, Mr. Dueck. Fine. F-app. This can't be correct. I can't be done. Why? What two words did we underline? Which means forces must be, are forces balanced right now? Vertically, yes. Horizontally, there has to be a force pointing backwards. Bigger, smaller, or the same size as F applied. What did you say about constant speed? Forces. So, got to be the same size. Everybody draw an arrow, eyeball yours, make it the same length as F applied, however long you drew it. What force is that? That's the thing that's resisting the sliding. That's today's topic. Okay? There's our quick free body diagram. Who's winning? It's a tie in this case. Why is it a tie? Constant speed. So here's what I can say. F applied has to equal friction. What did this question ask me to find, Nyla? Which of those two is how hard we need to pull? Well, F applied, I don't know F applied, but what's it the same size as? What does it equal? Friction equals what times what? From your formula sheet or from the box right above in the page? You can say mu. Yeah, friction equals mu times the normal force. So I'm going to say this on my next line. I'm going to move sideways so I can keep this all on one screen. F applied is going to be mu times the normal force. Hey, Nyla, what's mu? I don't know. What's mu with you? No, I'm sorry. What's mu from the question? They told me. Okay? I don't know the normal force. Oh, but look. I know another force that has to be exactly the same size as the normal force. Which one has to be exactly the same size as the normal force? Okay? There's our reasoning. I don't know there's no equation for normal force. Never gave you one in your formula sheet. But in this case, in this free body diagram, normal force has to be the same size as which one? So I'm going to say F applied in this case becomes mu mg. Let's do a quick double check. What's mu? I don't know what's mu with you. What's mu? Did they give me mu? Do I know m? Do I know g? We're home. Okay, that's the series of, yes, Robin, it's more than one step. I know you were complaining about that earlier. That's the series of reasoning we're going to do. Now we can plug and chug. So the mystery force coming from off the page, I've scrolled down. What's mu? I don't know what's mu with you. What's mu? Was it 0.65? 0.64? Thank you. What's m? They must have told me. 6.5? What's G? You've probably memorized it out of laziness. How hard must friction be pulling? Sorry, how hard must I be pulling to overcome friction and keep this moving at a constant speed? That big. You know what? That 2 now looks like a squared. I'm going to completely move this. I don't like that at all. There. That's still, well, there. What do you get? Owen, what'd you get? 40.8. Anybody else? It's Owen. Yeah? Okay. Back to you, Nyla. Units. It's a force. Yes? Let's pause and review here. So we said, in this case, because of constant speed, we know friction has to be the same size as F applied. I can't find F applied. That's what they want. But I know it's got to be the same size as friction. I got an equation for friction, mu times the normal force. I don't know the normal force. Oh, but look. I know the force the same size as the normal force. Got to be mg. So we're doing a lot of, well, it's got to be the same size as that, same size as that. We're doing a lot of, if you're doing systems of equations, we're using the substitution method for those of you who are scorekeeping at home. Holy smokes, Mr. Dueck, I'm writing a test on that if I'm Mr. Camosi's. Yeah, okay, anyways, turn the page. So we give a special name. Maliko, did that work okay? Or Oh, Dallas is the weak link in the chain? Okay, figure it out. We'll do the next one. We give a special name to an unknown source coming from off the page, from an outside source. We typically just call it the applied force, and it just comes from English. We say something's applying a force. Hey, let's call it the applied force. And the symbol I'll almost always use is FAP. Okay. Suppose we're pulling on a 6.5 kilogram mass across a rough surface. The coefficient of friction is 0.64 with an applied force of 86 newtons. Ooh, Megan, what does this want me to find? You know what this is a good job for? Yeah, although did they give me a picture? Okay. And I'm hopefully right around now, most of you are going to start to notice we're getting kind of repetitive. We're just tweaking things, but we're getting a standard method. We're going to do a free body diagram. What are the forces acting on this? Get the obvious one. Which way? Are we sinking into the ground like quicksand? Are we flying here like Superman? Vertically, forces are balanced, so there has to be an arrow pointing up, the same size as mg. Eyeball it. What force is that? That's going to be the surface preventing you from sinking into it, which we call the normal force. What else? They told me that there's an applied force, so I'll draw it pointing this way. I'll label it F applied, and I'll make a mental note. Hey, they even told me it's 86. What else? Do they want me to include friction? How do I know? Rough, or they gave me a coefficient of friction. Which way is this mass sliding? To the friction resist sliding. Which way is friction going to be pointing? Bigger, smaller, or the same size as F applied? I'm going to assume smaller because we're accelerating. What if they had said slowing down? What if they had said constant speed? There, that's it. Right there, Carly. That was everything. It's going to be slowing down, speeding up, or constant speed. Here, I'm going to make it stupid obvious, exaggerate so that I can clearly tell it's smaller. So, what does it want us to find? Did they give me a VI or a T? You know what? We're going to use winner minus loser. And we're going to use then Anderson's theorem to get the A by itself. Who's winning? Minus. Alexis, you didn't see. She looked at me and she was looking like, Mr. Dueck, come on, say who's the loser. Come on, say it, Mr. And she was just so disappointed because I hesitated. Okay, fine. Friction equals what? What did they ask me to find? You know what? Usually on this line, because I'm lazy, I already go boom, boom. Do I know F applied? Yeah, it's 86. Do I know how big friction is? Not yet, so let's keep going. If you want to, you can move down. I'm moving sideways to try and keep this all on my screen. And now, if you don't mind, I'm going to go A equals. I'll bring in the 86 on the next line. I'm going to do this still algebraically. Minus friction is what times what? Mu times the normal force. Let's walk through our mental checklist. Do I know F applied? Yep. Hey, what's mu? I don't know what's mu with you. Do I know mu? Yep. I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. Which one? Which force is the same size as the normal force? Yeah, or what two letters could you say if you wanted to suddenly stop and pause weirdly in the middle of a or oh, sorry? Okay, sorry. Yeah. So I can say this. A equals F applied minus mu mg. Mr. Dueck, won't it always be mu mg? No, I'm giving you easy ones right now where the normal force is equal to gravity. We'll have extra stuff where the normal force won't be equal to gravity. We'll have to do some thinking. All over m. Let's do our mental checklist. Megan, do I know F applied? Mu, m, g, m. We're home. We're home. Now it's time to plug in the numbers. It's going to be 86 minus, what's mu? I don't know. What's mu with you? Was it 0.64? Was m 6.5? Times 9.8, all divided by 6.5. All of you should try typing these into your calculator because this is only about a C plus level of the difficulty of stuff we're going to be typing in. Is this a fraction? Yes. Is there more than one thing on the top? Are there brackets around the top? Or if you have the fancy smancy fraction button, 6.9587 blah blah blah. 6.96. Okay. As a follow-up, could I now say, oh, assume we're going 2 meters per second in 12 seconds, how fast will we be traveling? I could all of the kinematic stuff now that we have A. Any equation with A on it would also be fair game. Is that right, Megan? Is that what you got? 6.96 meters per second squared? Example 4. Suppose we're pulling on a 6.5 kilogram mass across a rough surface with a force of 48 newtons. What's the acceleration? It's going to be really, really a similar setup. It's still going to be, Kanan, you know what this is a good job for? Yeah. What are the forces acting on this mass? Get the obvious one. What else? Yeah, and you can see this is why I'm teaching you to go systematically. Everyone wants to go to friction and F. Patience. Get all the obvious ones first. Normal force, same size as mg in this case. What do we call the mystery force coming from off the page? Good. What else? How do I know there's friction in this question? The word rough, or if they give me a coefficient of friction in the question or in the diagram. Bigger, smaller, or the same size as mg? I think smaller. I might be wrong, and I'll show you how we'll know if we're wrong, but I think it's smaller. Mr. Dueck, I think this is going to be exactly the same as the previous question. Yeah, but that's okay. Let's try and do it without looking at the previous question. What's my equation going to be, Kanan? Who's winning? Losing? Equals? What are we trying to find? I'm going to use Anderson's theorem and get the A by itself. And when I do that, I'm going to get A equals F applied. I'm not going to write friction. I'm going to write the equation for friction. By the way, hopefully you've all noticed where it is on your formula sheet. It's the third one. The first one says F net equals MA. The second one says FG equals weight equals mg. And then the third one says friction equals mu times the normal force. Mu times the normal force. A lot of you will memorize that third one out of laziness. Go ahead, but you don't need to. It is on your sheet. But probably if you do memorize friction out of laziness, you'll do yourself a solid. Divided by m. Let's do our checklist. Kanan, do I know F applied? Hey, what's mu? I don't know what's mu with you. Do I know mu? Do I know the normal force? Not yet. Okay, let's go back to my free body diagram. Ooh, oh, but look. I don't know the force the same size as the normal force. Which one has to be the same size as the normal force? Yep. Mr. Dueck, I'm telling you, I think the normal force is always going to be mg. It's because I'm giving you simple questions. I'm not having anything else lift up or push down. If you're wondering what we're going to start to do in a couple of days, we're going to be looking at situations where we have something else pushing down, like in this picture, or something else lifting up, like in this picture. And I'm telling you, then the normal force won't be mg. We'll actually have to calculate it, but we'll still be able to do that. That's what we're building towards, in case you're wondering, Carly. Let's go back to this one. So it's going to be A equals F applied minus mu mg all over m. Kanan, let's do our checklist. Do I know everything? It's going to, I've scrolled down. What was F applied? What's mu? Was it still 0.64? M, still 6.5. G, 9.8. All over 6.5. I told you earlier I wasn't sure if friction was bigger. Here's how you know. If you get a positive acceleration, you pick the right winner. I don't know. I'm deliberately not typing this in. What did you get when you typed this in? A positive answer? Got an error. You have to have. Positive answer? Okay. Is it 1.1 repeating? Or 1.1? No, it's 1.11. Okay, the fact that we got a positive answer, we picked the right winner. If you get a negative answer, don't panic. You picked the wrong winner. Friction should have been longer. Your equation should have been who's winning. Friction minus who's losing. F applied equals what, MA. And it's a pretty easy fix. So if you do get a negative acceleration, don't just ignore it. It means you picked the wrong winner. You got to go tweak some stuff. But it's only a tweak. For now, what'd you get? Oh, second time was the charm. And meters per second squared. We're going to temporarily press pause, but I'll show you a couple of videos since we have time.